Have you got any question about what we have seen up to now? No, it's too easy. You have to study to have questions, of course. But okay, so up to now we have seen the core of the basic, the fundamental basic of geodesy. We have seen about the figure of the Earth as we approximate the figure of the Earth, and of course also this in terms of figure, in terms of shape and size. We are going to speak about orientation because the figures of the Earth was shape, size and orientation of this surface. And so we discuss about shape, size. We have seen that we have different we can use different approximation, planar approximations, sphere and ellipsoidal, but for more detail we need another surface that's called geoid approximation, and it's related to the gravity field, and the gravity field is the other topics of the geodesy. Sorry. And now today we finish speaking about gravity. We introduce the gravity anomaly, and okay, space geodesy. Space geodesy started at the beginning of the 1980s because we start to use a satellite to perform a measure with the satellite. And is okay. Space geodesy means that we use satellites that could be artificial satellite, or can also be some natural satellite. We can put instrument on the moon or using quasar to perform measure. Quasar probably, and we are going to see out. So it means that we want to improve the knowledge of the Earth, but using information coming outside the Earth from the space. And as I already tell you, the satellite geodesy improve a lot of the knowledge of the about our planet, and it became very easy to perform. Expensive because we have to put satellite on space, of course, but from a theoretical point of view, once the satellite mission is started, it's very easy to perform measure, to repeat measure, to have an homogeneous precision all over the world. Otherwise, it depends. If you look at a map, for instance, of the gravity measure, you see a lot of gap over the Earth in the desert part, the part with in the high mountains, part with in Antarctica. We don't have so much information as for instance we have in Europe, we have also in the USA and so on. It depends also by the country, you know, to perform measure we need money, and so it depends also by the economical condition of the country. And so with the satellite mission we overcome all this problem, and we can perform a measure in an homogeneous way. And at the beginning we use existing astronomical equipment or radio telescope used for instance for astrophysics study. And in the last years, we started to put dedicated satellite for the study of the gravity field, but also satellite for GPS measurement, or satellite to perform InSAR measurements. So in the last 20 years, no, the GPS is older, but the big development we have with the satellite we have in the last 20 years, we are going to see more or less the time passes quickly. So, but in the last 20 years we improve a lot of the satellite mission for the studies, for the Earth observation, as we call it. Okay, what we can obtain by satellite geodesy, we can obtain information on positioning. In this category we can put GPS, but also other techniques that we are going to just to introduce, like a satellite laser ranging or VLBI. That is a technique that we share with the astrophysics community, and so on. We can use radar altimetry. I already told about radar altimetry to see how I can measure the sea level, the surface of the surface of the oceans. And we can use interferometric synthetic radar apertures. We are going to see that these techniques are quite correlated because both use a radar as an instrument, but are quite different. So we are going to see in detail these techniques, because with the GPS are the two techniques that are more used for the physical application. And gravity studies. Now we are going to see this part, so we can conclude this part on the gravity field of the Earth. From the lesson of tomorrow we are going to see just the problem related to the positioning, so with the GPS technique. Okay, we have seen that gravity is important for many applications. For geoid undulation estimate, as we have seen, to compute the geoid undulation, we need gravity observation. And this gravity observation can obtained by ground station or satellite mission. And I use gravity to estimate geoid undulation estimate. Is my PhD thesis, the estimate of geoid undulation for the Italy. And so from the beginning, I see the gravity field and the problem related to the deformation, gravity and geometry in some, and there is a lot of theoretical connection. Also, is the way how we handle this data. We have a huge quantity of gravity data, and we have to treat it in a using statistic techniques, using stochastic processes and so on. And we don't use just closed mathematical formula, but our approach from Polytechnic of Milan as a research group, use statistical instrument. And now when you purchase GPS time series, more or less you have the same problem. Now we have longer and longer time series of data and bigger network of GPS station. So sometimes now we are able to see very small deformation, and often to see this small deformation that in the same order of magnitude of the noise, you need statistic methods. So I found a lot of things in common between the two approaches. It's different, of course, the result is completely different, but the approach to the data in some applications is very similar. Okay, this is, sorry, just an introduction. Okay, we use gravity for investigation of the crustal structure to know the density. What means that we want to know the density of the crust. And we have seen that we have gravity observation. The gravity field is related, if you remember, to the formula, but from the gravitational law by the mass. And in the mass we can express the mass in terms of density. So this is one of the tasks of the investigation of the crustal structure. Or we can use gravity for interpolation, extrapolation, okay, to have other type of information related to the gravity field. Usually, to use gravity data, we have to reduce the gravity. We have seen just what you have already seen one reduction. We started from the G values measure, and we obtain the gravity anomaly, reducing for the normal gravity. I probably have to put here again the formula, because it was in the previous lesson. So we have seen the first reduction was the gravity anomaly. I already write in the book, but today I'm going to repair it. This is the gravity anomaly. I reduce from the gravity the values of the normal gravity. The gravity predicted by defined by knowing the dimension of the ellipsoid, the size of the ellipsoid. That we see that in this ellipsoid are included all the masses of the Earth. So this is the first reduction that we have seen. But often we need other reduction. We need to reduce our measures that are performed along the Earth surface, the topographic surface of the Earth. We have to reduce to the geoid, to the sea level, to say in a simple way. When you have you see to observation in geophysics, you also refer to the sea level, not to the true topography. So what we have to do is like to remove this the effect of this mass, and we have to do two things: reduce the effect of these masses between the topography surface and geoid surface, and if you cancel or reduce for these green masses, you obtain a point on the Earth surface in the air. So we have to translate this point on the geoid. And of course, because the gravity field is related to the distance between the masses, we have to reduce for these distances between the point P and the mass of the Earth. So this is called Fourier reduction, moving this point on the geoid. We are going to see. So this is the Fourier reduction. We have removed, we are going to see how the masses between the Earth surface and the geoid. And now we have to move downward to the geoid. And this can be done if you consider a Taylor expansion of the gravity. We can see that this is given by the gravity on the geoid, and the other term related to the height, to the gradient of the gravity with respect to the orthometric height. And what we obtain this term is called Fourier reduction. And it's given by this value, 0.3086 multiply the height of the point. And usually in geodesy we use as a unit the gal. One gal is centimeter over second square. is 1 gal, but often we deal with milligal. Why we deal with milligal and not with gal? It's related to the fact that we are using gravity anomaly. So we already reduced for the big part of the gravity related to that we can approximate with an ellipsoid, with the gravity, normal gravity. So what we attain is smaller values. That this is the reason we usually have a milligal, 10⁻³ gal. Okay, so this is the first reduction. To translate the gravity from the surface to the geoid, where if between the 2 points we don't have masses. Now we are going to see how to reduce for these masses. I know that the people that are well, just you and the people, the guy for the PhD courses. For you, it's the first time that you know about Bouquet anomaly, I think. Okay. So if if I go too fast, please stop me. Okay. Because for him probably are very easy, already seen. No? Okay. Because it's a part of the classical solid earth course. I start, so you have to refresh. Okay. So, important reduction really used for in geophysics is the Bouquet reduction. Usually when you speak about gravity with the people from the geophysical community, you speak about Bouquet anomaly. When we speak with the people from geodesy, we speak about gravity anomaly. We don't perform Bouquet anomaly because for us it's important the gravity anomaly to compute, for instance, geoid. But for geophysical application, it's important to use Bouquet. So this is the first differences, and when we speak about with people from geophysics, we have to take him in our mind. They speak about Bouquet, we speak about gravity anomaly. It's not a problem, but just to say we have to speak the same language, of course. So, with this reduction, we want to remove for the topographic masses. Why? Because often we are interested in what happened in the crust. And if you remove the masses that in some way you can model, we can see that there are some approximation, because also in the first part of the surface of the Earth we can have different geological composition of the Earth, of course, but often we want to study a deeper structure. So if I remove the masses outside the Earth, I can study what happened inside the Earth. Because if I am in a point of the, what we want to do if you are on the Earth surface, your gravity measure will be affected by, for instance, mountains close to Trieste. We know that this mountain has effect on the gravity because our masses, of course, everything has effect on the gravity field. But if I remove this part, I have a signal that depends on just on what we have behind our feet. In the crust. So we want to investigate what is under the sea level, under the geoid level. The geoid represents for us h equal to 0. Okay, I remove all the topographic masses. So the simple thing to do is use a Bouquet plate. We remove the effect of this infinite plate by in terms of gravity. So we have a measure in the point P. We can reduce for this that is the attraction of an infinite Bouquet plate. Due to this plate with height equal to the height of the point P. This is a very simple formula, and it depends. You can see that it depends on the density. So you are doing an approximation, which means that this layer is an infinite layer, and we have a constant density given by these values. If we use a standard density values, we know that we can compute, because the other one are constant values, that the Bouquet effect is given by 0.1119 multiplied the height of the point, and the height has to be given applied in meters. You have just to check, of course, the magnitude of the quantities that you are using. So this is from your gravity point, you can remove all the masses, reducing for this quantity, your gravity minus this quantity. This equation is given, you can compute this why we obtain this very simple formula, and it's given by computing the effect of a cylinder, or like this one, and you compute this is the potential due to this cylinder. We know the density we fix, and we have L is the distance, and knowing the geometric quantity, we can compute this this computation. And if the point P is on the cylinder, we can obtain this formula when the plate comes to infinite, A tend to infinite, and we obtain this. There is also a spherical Bouquet plate, because we see up to now we are thinking using a flat Earth, but we know is just a raw approximation. We can use spherical Bouquet plate, especially when we are using a huge area of the Earth, so you can feel the curvature of the Earth. That is a very similar formula, but with 4 instead of 2. So if you want, you can really compute all this integral. I just give you because most of us are physics or mathematics, and so from a scientific faculty we like to know why we obtain a very simple formula, and we say, okay, this is the result. So you can compute starting from this, the effect of the effect in terms of gravity of this cylinder on a point P, and the point P is outside the cylinder. And after you can think that the dimension of this cylinder go to infinite. Okay, B here is the height of the cylinder. In this case, in our case, is the height of the point. Okay. So we started from our gravity. We remove the Bouquet plate. We correct for the free air correction, because now we have removed all the masses between the point as the Earth surface. But we have to move downward the point from the free air, of course, and the Earth surface. And this is called phi f, that we have seen before. But what happened? This is called incomplete Bouquet reduction. Why? To have the Bouquet gravity anomaly. Anomaly means that I'm going to remove the normal field, gamma. Okay? This is the Bouquet reduction. This is the Bouquet gravity anomaly. Anomaly also with respect to the normal field. doing this was happened that if we have this, okay, this is the point. The green line is your Earth surface, your topography. You are in a slow plane, more or less. And you have removed, in this case, here you have masses, and here you don't have masses. Removing a plane is like you have added some masses here, and you don't have removed for the masses here, because it's a gravity field. So we are speaking about vector. So these masses, these points feel the attraction of this mass, and this point don't feel the attraction of this mass, because isn't this mass is an artificial that we put mass here, but we don't consider masses above. So we have to compensate this effect. In one case we have removed, like we have masses. In another case we don't consider that the point P feels the attraction of these masses. In this case the vector is in this direction. Okay. So we need to refine the Bouquet gravity anomaly. How we refine the Bouquet? Sorry that I check. Okay, a lot of complication. Okay. How we can correct this? We are going to model our topography. If you think that you can discretize your topography surface, we have what we call a digital terrain model. A digital terrain model is a grid, a regular grid, in a normal case, is a grid with some cell, with width and length, and you can see how your Earth surface is given by this model. It means that this regular grid, in each node or to the center of the cell, this is a convention. It depends how to you write the grid, but it's not important. For me, it's easier to thinking about the grid node. You have a height, for instance, 100 meter, 101 meter, 102 meter, 99 meter, and so on. So you have a discretization of the Earth surface. This is called digital terrain model. We use a lot of digital terrain model. The simple application is to put a beautiful figure in your paper. Often it's important to see the correlation of your data with the Earth topography. So we put a beautiful figure with some contour line. No, it's not contour line, it's better now, with some figure that you can see the topography under your measure point. But we use this digital terrain model also for computation, because it's a discretization of the surface. So if I know a digital terrain model, we are going to see that it is one of the most important product of an important SAR mission. We are going to see in this lesson. Now we have data from this SAR mission. Sorry, I forgot to switch. No, sorry. You see, it's difficult to to do lesson and to see into the recorder. Sorry. And so now we have a global digital terrain model with a good resolution of 3 seconds or second, yes, or 1 second. So it means 90 meters or 30 meters. So it depends on. It was performed by the NASA, and at the beginning they give realize just the solution with 3 seconds of resolution. So it means about 90 meters of resolution. It means that every 90 meters we have values for the height of the Earth's surface. So it's important. More or less, moreover, the world, we are going to see that it's not cover all the world. And if we have this type of model, we can compute the effect of this type of parallelepiped. Parallelepiped is similar Italian, sorry. On the point P, in terms of gravity, and with respect to the height of the point, we know if we have to add this, reduce for this effect or add this effect. So we can compute the Bouquet, removing a plate, and after correct for the difference. I remove too much masses, so I have to correct for this, or I don't remove for important masses, so I have to correct for this. And this is called terrain correction or topographic correction. We can also start it directly by this approach without removing the plate, but model the effect of the topographic max on the point directly. We can do in 2 steps. One is remove the plate. I'm going to correct where I put too much masses or where I remove too much masses. And otherwise, I can start it by a DTM and compute this effect on a point, correct for it. And of course, we have to take into account where we are on with a height, positive height, it means outside the sea level, or when we have a zone with water, we have to use different, of course, density, because if the density of the crust we have seen is more or less is depend on the zone. The mean values is 2.67 centimeter over gram over centimeter. In my mind the unit of the gallons, I don't know what I say, and okay, gram over centimeters cube. And okay, and for the water, of course, the density is more or less equal to 1, is 1.001 if I remember. If you have ice, it's a bit less than 1, is 0.99 every time I check this value, of course. So in this case, you have to refine, and you have to compute the effect of each parallelogram on parallelepiped on your point, and sum all this effect. So if I have a point here, I'm going to compute the effect of each parallelogram on the point, for instance, P point in this position. And of course, the parallel can be higher or lower than the point P, of course. Here you can find the formula. This is the potential of a parallelepiped computed in the point P, in a given point P. Okay, a lot of formula, and at the end we arrive to this solution where the function f is given by this relationship. And of course it depends on the density. We decide the density. When you compute a Bouquet, you have to have an idea of the density or the mean density of the area that we are considering. You can do also, there are some papers in literature that they use different values of the density and explain method to find the best one. You have like to try different value and to see which value reduce better your data, give you more data with a higher quality in terms of statistic. And okay, now we are speaking about parallelepiped. To be honest, now because the height could be very high, of course, we can see the effect of the curvature of the Earth. So now there are some routines that can compute not the effect of the regular parallelepiped, but the effect of tesseract using, so you can take into account of the convergence when you go down towards the center of the Earth, even if you stop at the crust. So it's more, if you use a big size, 1 degree is not correct to use 1 degree, but probably in some global application you can compute 1 degree using 1 degree effect. You have problem when you go down, because in 1 degree you can record the curvature of the Earth. 1 degree is more or less, it depends on, okay, it's more or less dependent of the latitude, of course, but it's 110 kilometers to our latitude in Trieste, for instance. So you see, are very big, and probably you can see the fact that from point to another the Earth is not flat. So at the end, this is our digital terrain model. This is the point. We have to compute the effect of all these elements. And of course, and you have to sum all this, and you have the effect, the terrain correction, due to the topography, recorded to the point P. Everyone, when you deal with gravity, you have integral from minus to plus infinitive. So to be really correct, we have to use all the data all over the world. But for you can, while the effect depends to the square of the inverse of the distance, of course, the effect. A point in the south of Italy is so far from Trieste that we can neglect the fact of the Etna. It's a volcanoes in the south of Italy, that is a big mountains in the south. We can neglect when we compute the terrain correction for a point in Trieste. I put 100 kilometers, but to be honest, now we prefer to have a bigger zone, to arrive to 150 kilometers. So it's better to have a bigger zone than a smaller one. In the past, this was a time consuming in terms of computation, of course. Now with we have a very high computing capacity, so we can improve the zone. I remember when I started to compute the geoid for the Italy, we don't compute the terrain correction because we don't use this quantity for geoid computation. We use the residual terrain correction. It's another function, because okay, I don't want to. Okay, is related to the global geopotential field. It's another thing, but more or less the computation is started from a digital terrain model, and we compute the effect. It's like this, but it's not all the quantity between the topography to the geoid. It's a smaller part. Is the part that we think that we cannot see in the global geopotential model. So the high frequency of the topography that is not seen by the global potential model. We are going to fit this part, okay, but it's for geocomputation, it's not the point now. At the time when I started, when I was a PhD student, we took a lot of time, we consumed a long part of our computation was in computer this correlation, and I use different computer. We don't use programming. Probably you are not born. We don't use sophisticated programming with parallel, but it's like manual parallel. You say, okay, from this point to another point, I use this server, this PC. For another point, and then at the end I collect. And there was a nightmare because you take 1 month, 2 months of computation before to have the results. Now I can do the same with my laptop, more or less. So now it's not so a big problem. So I see that this distance is better to increase, and there are a lot of paper that show that it's better to arrive to 150 kilometers from the points to consider the effect. And if you don't have a computation problem, put inside, use a larger circle. And you can see also that in this formula is a convolution integral. So it can also solve using Fourier transform and fast Fourier transform. But if you started from the gridded data, okay, the digital terrain model, of course, is the gridded data, but the point where you compute this effect could be not a gridded grid. If you have a grid of point, you can use, for instance, fast Fourier transform, because this is a convolution integral. So it is faster. It depends. If you have measure point, I don't like to grid data, use it, because you move your data. Greedy is not, you change your data, so it depends. You have to put you have to be very careful in gridding, because you can change where the point is, and you can introduce misunderstanding different features. So, but if you have gridded data, or more or less gridded data, if you have a dense set of data, you can grid the data and you can check if the gridding is good or not. You can improve the computation with fast Fourier transform. I don't put the formula, but I think that you know what is a fast Fourier. A Fourier transform, I'm sure that you know what is. A fast Fourier is a technique when you have gridded data to improve the computation.
Can I ask?
Yes.
What about the sum of the all parallel types? I mean, there is a weight for each parallel types,
no,
related to the distance, I mean, between the parallel types.
It's given by the formula, because in the formula is implicit the distance between, you can see differences in the coordinates.
Okay.
So you use, these are coordinates, the coordinates of the point P and the coordinates of each parallel peep. So when the parallel peep are far from the point, is automatic, is reduced, is weighted inside the formula.
Okay. Thank you.
Okay. What this is for the Bouquet anomaly. I don't. So this is I remember also last year I realized that I don't put the final formula. Okay, I'm going to improve the slide. So we are here. Incomplete Bouquet reduction, we have to add the term AT, the terrain correction. So after I'm going to correct, no, not to correct, to improve the final. The final is, given the gravity observed, I'm going to reduce for the bouquet and plate, I'm going to reduce for a terrain correction, I'm going to reduce for the free air. Okay, this is all the term together. I'm going to put another slide. Okay. This is, so we have seen the Bouquet anomaly. It's clear what we obtain and all the steps, more or less. So I know that you need to read the slide and to really understand. But so we want to reduce the topography effect. And thinking and working with a flat earth without topography, without mountains, without valleys, or so on, without ocean. We have an homogeneous earth with a given density, at least for this part that we have removed or added in the case of the basin. Okay. What we can see is, if you look, this is the Bouquet anomaly for the gravity data. You can see some line because this is computer using not gridded data but using the observation. For each point of observation, I compute the Bouquet anomalies. So you can see here a regular distribution because we have dense gravity data set in the Italy, in the peninsula part. We have some problems along the Alps because it's not easy to do gravity measurements, and in some part in the outside the Italian Sea we have some data given by, for instance, BGA, a service of the IAG that collected gravity data, and you can see line because as the ship track are measured performed by ship on ship. And also here in Africa we need data all around the Italy, but in the foreign country we have less data, of course. And you can see that, you know, we are here in Trieste, and these are the Alps. The Alps are in the Alps there are the highest mountains in Italy. And you can see that in this part, the Bouquet anomaly, we have the strong negative values of the Bouquet anomalies in this part. Also here we have the Apennines, and we can see all the Apennines more or less, and so. And when we have in the basin, we have high positive values of the Bouquet anomaly. So the Bouquet anomaly are negatively correlated to the height. And this is because we forgot the isostatic compensation. We have forgot that under this, this is the surface topography, this is the geoid, but the mountains don't finish at the geoid, but have some roots inside the earth. So we have to, like when it's an isostatic problem, like when we have an iceberg on the sea, we can see a part, and below the sea level we have the bigger, in that case, the bigger part of the masses. And so we have to consider another reduction. There is a static, compensation. There are different. This is a plot of the isostatic, if I remember, compensation. Yes, we have two different approaches to model this effect. So we are going to say that, okay, if we have mountains, the mountains are also below the geoid level. And how we can model this effect? There is two different approaches. One is a Pratt-Hayford system approach. They consider a constant level of compensation. We are going to see in the figure, and use different densities for the masses. And instead of the highly scattering system, that they use the principle of the floating. So they put a different compensation level, but with the same density of the material, of the masses. We are going to see. So in the Pratt-Hayford system, sorry, we have a constant level of compensation at a given distance, d. Often use minus 30 kilometers as this depth. And this, in this case, for instance, this is the geoid. We have some topography, and we have a basin, some sea. So, no, this is 100 kilometers. Sorry, yes, I did a mistake. 100 kilometers, and it's okay. He uses the principle of the masses conservation. So he says the mass of each column has to be constant to have the same level of compensation. So this means that the density is changing column by column if the mass has to be the same, and we have different height or also different composition. So these are okay. So when we have a topography with it means that the automatic height is greater than 0. We have a mass deficiency in beneath the column. So you have to, if you consider the case of a reference case where you have you don't have topography and you don't have sea basin. So you put a reference density equal to 2.67. So if you have mountains below, upstairs, you have to reduce the density to have the same masses between these two columns, and so on. And in the opposite, when you have water we know that have a lower density. So it means that we have to increase the density of the column under the water. And what these differences in the density values could be computed, it's equal to this formula. The density variation with respect to rho zeros is given by the height of the point over this depth d plus the height multiply for rho zero. This is because we want that the masses, these masses, will be equal to these masses. This relationship derived by this condition about the conservation of the masses. Okay. Now we look at the case when we have water. Here, In this case, it's more complicated because we have to consider the fact that we have a part with the water, so the density of the water multiplied for the depth of the basin, and we have to take into account for this residual column under the water. And this have to be equal to our references when you don't have topography. And from this relationship, you obtain this is the density of the water. You obtain this variation in the density. So, just a moment. Okay. So it means that if you want to compute the effect of this compensation, you have to consider this variation in the density. And you use the same approach that we have seen before with I'm going to model all my parallelepiped with this density, variation on the density. Okay, in the higher scanning system, as if I remember, Harry at the idea is scanning were more precise in the mathematical model, if I remember, but it's not important. They have to name for this reason. They arrive to the same model, but with two different contribute. Okay, in this case, we have a different compensation depths. It depends on the topography. If you have, for instance, if you don't have topography, for instance, you have a height of 30 kilometers, and when you have topography, for instance, you have a root in the depth that depend on the height on the surface. It's quite clear. It's not, of course, the same height. We don't have 2 kilometers, we have, for instance, 8.9 kilometers, but it's related to this quantity. In this case, we consider a constant density for the crust and a different density for the mantles. It's a floating theory. It says that we have a less denser quantity over a denser material, the mantle, and is a floating balance. And we have roots that depend on this quantity. We are going to see. And the same when we have the water, we have anti-roots with respect to the mean density, the mean depth.
Excuse me.
Yes.
I don't understand in which case I should use every model.
We are going to see that there are different experiments. In some part of the world is better one system, another better. Recently I read there was a distinction. I think that in average the Hardy model fit better, but usually it's not a rule. You have to check. And I don't remember, but there is, if I remember if it's related to the ocean or less, you can guess which one is better or not. You can trust.
I would say it depends on the degree of isostatic compensation. For example, if it's fully compensated, that is the every one. If it's not compensated, I use the first one.
I think no, because all the hearts is quite well compensated, to be honest, for the night. If I remember, probably I put the number in the slide. If I remember, 19% of the heart is isostatic compensated. So usually this is my approach. To be sure, you have to try. So it depends zone by zone and so on. You have to try. You can use an approach, another. You have to go to see the residual. Usually, if your residual is your data have a residual more smooth with a mean and average values that goes through the zero, and a standard deviation that is reduced, and a minimum maximum values that is reduced, probably you are in the right direction. So you have to check and see what is the best solution. But I don't remember, because in the I processing data in Antarctica, and to compute the Moho surface, and I use gravity, and we combine with seismic data. And just to study this problem, because in Antarctica we have to take into account for height and so on, I start again to read about isostatic, and I find some information about this, some general information, when it's better to use one or another. I'm going to check if you are interested, because you are working on glacier isostatic adjustment, so if you are working with George Spada, of course. You was working, okay, yes. But okay, also in isostasy, you have to take into account for the time, because there is an effect for the past and an effect for the present. So it's difficult to distinguish these two quantities, because now we have ice melting. So in some part of the world we are increasing the. Yes, we have a post-glacial rebound. Yes, in fact, when you talk with the people that are studying this type of problem, sea level problem, now they say it's not important, generally speaking, the global sea level change. It's important the local sea level change, because we have part of the Earth where we have an uplift, another part where we have download, because you don't have rebound, so you have the effect just for the ice melting, so the sea levels that increase. So it's more complicated, all of course, of like everything in the Earth, to have a general law about this problem. We know the trend, but the answer could be different. It depends on the part of the world. So I'm going to check if I found it. And so we say that we want to have this is the condition to have a floating equilibrium. Is that the T is these steps given by the product, these masses given by these steps multiply the differences between the two densities have to be equal to the height multiplied for the density, the reference density, the density of this part of the crust. This is the floating equilibrium. So from this relationship we obtain the values of the root. So the thickness under the mountains is given by, if you are on the top, is given by the automatic height, this medium value is T, plus the root depth. We obtain this. And you can see that if you use standard values as this one reported in the plot, you have 4.45 multiply the height of the topography. Okay, this is on the when you have a height greater than 0. Now we have to see what happens when you are here. You have to reduce. Oh. Sorry. I'm going to. When you are on the sea. And in this case, the floating equilibrium equation is this one, when you have to consider the differences between the density of the crust with the density of the water, and you have to compensate this quantity. And this is the formula that you obtain. So for each point you have to check where you are and which correction you have to, the water and the H greater 0 or the H less 0, you have to deal in a different way to find the thickness of the crust. Have you got questions? Probably now you feel a bit confused. I suppose you have to check the equation and. Okay, I'm going to send you the slide so you can see with your time the formula, and you can write me or you can ask in the next lesson. Okay, in the Harry approach, as you see, there is a rough model of the surface. There is an improvement of the model, the vanning, I don't know how to say this, no, minus, but I'm not sure about the pronounce, that in 1931 introduced a regional compensation or local compensation. So also other research smooth this quantity. It's using a low pass filter to have a more regular, more smooth surface, because you can, okay, this type of discretization is easier for our computation, but we don't expect that in the nature we have this very sharp figure. So they introduce a local compensation, introduce for it a low pass filter to have a more regular surface, compensation surface. Okay, now we can use spherical correction to the formula to take into account for the curvature or the hertz. The hertz is 90% isostatically compensated. Seismic results indicate an RE type of compensation. In some places, the compensation seems to follow the Pratt model. I have to check where one of the two, if we have some information. In the last year, a lot of researchers are studying again the isostatic problem. So I see that they are introduced different type of correction, but the two principal idea is a Pratt or Henry compensation. The other one are refinement of this model, more or less. But there is in the last year I found a lot of paper. Now, in this last part of the lesson, to conclude the part of the gravity, yes. After we are going to speak about deformation, GPS, and so on. GPS and after deformation, I'm going to present you just the gravity satellite mission. But I think that you can find a lot of in a lot of papers that you read probably are. They speak about this result. And okay, the first one of the most important mission is the GRACE, Gravity Recovery and Climate Experiment, and has been performed by NASA and DLR, German Space Agency, and it started in 2002. Now I have to check. Ecco, Grace Follow mission is scheduled for launch in 2017. When you have a satellite mission has a lifetime. It's not a work forever. And for the Grace, because it was a very important mission with a very good result, they decided to schedule a follow-on mission, to continuous. The problem for the scientific community was to reduce the gap between one mission to another mission, to don't have a gap in the data, because the gap in the time series are not so good. You have to extrapolate, you miss information. It's not easy to connect one part to another part, especially when you don't have just a linear trend in your time series. So to be honest, I didn't check if this mission is started or not, because in the last, usually I attend a different lot of meeting of Geodesy, but in the last year I didn't. So I have to check if this follow-up mission is started or not. But you can find this information using the website of the ESA, the European Space Agency. You find a lot of information about the mission, all the mission performed by the European Space Agency, ESA. ESA. And okay, in the Green mission we have two satellites that are working in pair, and it's important that they are working together because they want to record the variation in the gravity field. So I need to have a satellite that perform a measure. After a given time, we have another satellite that repeats the measure. With the Grace, for instance, the Tohoku earthquakes can be recorded. Not all the earthquakes, it depends on the magnitude. But with this system, when we have so big events, seismic event, the satellite can record this event. And it's important is a called low mode. It means that we have a GPS satellite. Okay, we are going to see what is a GPS satellite of all the characteristics. But we know that the GPS gives us the position. It gives us the position on the Earth, but also on the space. So give position to the satellite, because on the satellite we have a GPS antenna. So we know the position of this satellite using GPS. And of course GPS are connected with the ground station, but it's not important. And this is called satellite to satellite tracking low mode, because are controlled by the satellite that are above, but it's not important. And we have two types of satellite. The altitude is 500 kilometers, more or less is the altitude of the old gravity's mission. So you want to measure the variation in the gravity field, and also give us information, because they put in instrument about ionosphere and troposphere. There are two layers of the atmosphere. We are going to speak with the GPS about the ionosphere and troposphere, because they are also important for the GPS data analysis, taking into account for these two layers of the atmosphere. So the instrument on board of a Grace satellite are GPS, accelerometer, we are going to see what is, ultra stable oscillator to give measure of time, star camera to also give a position with respect to the stars, and laser radar reflector to be tracked. The satellite could be tracked also by the Earth using a laser measure. If you have some mirror reflector on the satellite with a special station from the Earth, you can track the satellite, check where the satellite is. This is really important for gravity measurement. K-band ranging system, if I remember, at the moment I'm not sure, is to measure the distance between the two satellites of this pair of satellites of the system. They give us monthly global gravity maps with a resolution of about 30 kilometers, 300 kilometer or 400 kilometer on the ground. So it is important. With the GRACE we have important information on our average over a month. And the resolution on the Earth is about 300 kilometers. So it means that we see important change in the Earth. So the gravity field. So an earthquake of magnitude 5 don't affect the Earth with this scale of resolution. We know the deformation is around 20 kilometers, 30 kilometers, 50 kilometers, but not the 300 kilometers. So it's difficult to map. Okay. They give information about static global gravity field. Okay, static means what is not changed over time. It means important information about the low degree of the spherical harmonic expansion of the gravity field. We don't expect a lot of change by the core, by the lower part of the mantle of the Earth. In this part we call static global gravity field. GRACE is able to monitor fluctuation in the gravity field due to a different masses distribution. Different masses distribution from one satellite to the other satellite. During this path, if something changes, the second satellite have different observation with respect to the first one. So I can control, record these differences. Okay, so it's important to study current in the ocean that have that change over time, over in a month or less, or groundwater storage on land basin and so on. But I'm going to see some application. Okay, these are this champ was another gravity mission. Now we are going not to speak about this. This gravity mission is finished, but we can see the improvement. This is the geoid ondulation. In fact, we have a meter as a unit, and you can see this was one of the first figure, because 110 days of GRACE data. We can see just the difference. You have more features in this model than in this one. You can see. So this is based on 33 months of data. So more than this 110 days. I really remember this difference. So okay, we have a good resolution of the static gravity field. And about variation, this is from a paper of the University of Texas. I think that if you want to see the paper, you can find in an easy way. And this is May, June, July, August, September, October, November, December in 2004. It's quite old. It was at the beginning of GRACE. As is the variation. This is water layer height. The height of the water layer in centimeters, and you see the variation during the seasons. So I remember that when these results were presented in the meeting, in the workshop, I don't remember which one, probably in in IAG meeting was the people were really impressive because you can see centimeter variation. Of course, this is Brazil, is Amazonia, and you have a big effect for water and so on. And also Brazil is very big, so you can see in Italy it's not easy to see this picture because from the north part of Italy is wide, I think, 300 kilometers. So you have a resolution of 400. But something you can see also in this part due to water variation. I did some work and some comparison with GPS and GRACE predicted. Of course, GRACE gives us information on the gravity. This information are translated in water layer height, in uplift or in uplift, it depends on the sign, of course, in high variations, that is better. And when you do this, you need to know something about the elastic, for instance, or viscoelastic response of the Earth crust. So it's not so easy, and you have to do some hypothesis to do this, but it's really an important instrument, and you can see, okay, this variation of small quantity, because 20 centimeters seems a big quantity, but it's not a big quantity. If you record this from 500 kilometers in the space, it's incredible. Okay, to finish, GOES, Gravity Field and Steady State Ocean Circulation Explorer, was an experiment of European Space Agency, and it's a mission that is close, is finished. They have planned to do measure from 2009 to 2030, more or less. And the satellite studies the gravity field of the Earth, so not the variation. It was not the task of this mission. Is to have the higher resolution of the gravity field from the space. It was a really dedicated gravity mission, and there is just one satellite with a notice accelerometer and gradiometry. If I remember, I put information, but no, I removed. Okay. Okay, accelerometer and gradiometry are two different types of instruments. Accelerometer measures just the acceleration, like uses spring, is normal as also all the instruments that measure gravity have spring. And the gradiometer use pair of springs, a pair of accelerometer, so give information in all the directions, the three directions. It's a more complete information about the gravity field in all the directions. Three pair of identical accelerometer which form three gradiometry arms, of course in each three. Yes. Mounted in an ultra-stable structure. This was the altitude so low. I'm not sure that's altitude. I have to check because if I remember, in my former university at Politecnico of Milano was one of the center to data processing for GOES. If I remember, this was not the final altitude. I have to check because there was some problem in the window they put in orbit the satellite. If I remember, the altitude was higher, but I have to check because it's time that I don't speak about this. The inclination okay, we need polar orbit, but it's difficult to have polar orbit. Every time these are not polar orbit means that I go through the pole, but it's not so easy. I think that some, I'm not sure about what the reason. I think that's a technical problem. So usually the orbit are quasi-circular orbit with a little inclination. And it was 20 months of mission, and after the mission, when the satellite stopped, it come lower and lower in the atmosphere, and the researchers are very interested for the data of the satellite closer to the Earth, of course, because you can record a more higher frequency. Of course, when you put a satellite, you have to put the satellite in the right position or in the right orbit to check while the position of the satellite. We had problem with the atmospheric drag, with the sun, and so on. So you have to find the best position. But when the satellite started to come down, the scientists are really happy because they want to see the data with a high resolution and so on. And it's a high-low mode because we use satellite, and we also use gradiometry inside. And I don't remember high-low mode. Why? Because the GPS satellite was up, high, and the GOES was down. The other one was, I don't remember, low. I don't remember why we call it in a different way. Sorry. It's just related to the satellite who check. I go to check, and sorry, I give you the answer. I don't remember. Okay, what we want to obtain a global model at high accuracy. We obtain 1-2 Joyce error. No, it's not true. We don't have with just GOES data a geoid with 1-2 centimeter of precision. This is a theoretical precision, but in practice we don't obtain this precision just using GOES data. But they really improve the quality of our knowledge in the gravity field. I use just data from in some part of the Earth. We don't have ground observation. That I realized that using GOES observation you have more or less the same quality that using a global geopotential model that try to extrapolate information in this part of the Earth. So in some part where, for instance, Saudi Arabia, high computer geoid for Saudi Arabia, the GOES give us a really good model. With the ground data, ground observation, it will just improve a bit the quality of the geoid, but it was a special zone, very local. So we have GPS, laser retro reflector, satellite altitude control, gradiometer. Okay, it's used for GOES is used also for oceanography. In fact, it was one of the application of probably time. So with altimetry, we can compute the ellipsoidal height. With GOES, we had the geoid ondulation. And so we can compute, no, sorry, not the ellipsoid, yes, it was an ellipsoid, no. We have the height of the sea, the mean sea surface geodesy. And often it's important to know the sea surface topography. Okay, we have seen that the geoid is a equipotential surface of the gravity field. The ocean, because are made by water, are along this surface, equipotential surface. But this is just an approximation, because we have we have a strong current that produces like a topography of the sea. You've seen the current, the Gulf Stream, for instance, is a big quantity of water, give us like a topography. So with combining, for instance, these two information, we have information about the sea surface topography. So the quantity of water, and for oceanographic application is really important. Okay. Oh, just in time. Okay.